Hi, my name is Sam and I'm presenting probabilistic verification of network configurations. This is joint work with my colleagues from ETH Zurich, Timon, Petar, Laurent and Martin. Traditionally, network verification is concerned with checking properties, such as reachability in this example here. As network components such as links are subject to failures, one often also considers those when verifying properties. There is a long line of work dealing with this task, and you can use these tools to answer questions such as whether the property holds for a specific failure scenario or for all scenarios in some set, including maybe all scenarios with up to k-link failures. As in this case, the property either does or does not hold for the whole set of considered scenarios, we call such properties hard properties. So in reality, the failures within a network are probabilistic, so link and node failures are the result of a random process. So we can lift the question of whether the property holds to this probabilistic setting and instead ask the question, what is the probability that the property holds? This is a very practical question. So for instance, consider an operator wanting to verify a service level agreement that with 99.99% probability or fraction of time, some prefix is reachable. Also, other properties can be analyzed probabilistically. So for instance, assume that the operator wants the traffic to be load balanced, not 100% of the time because this would be too expensive, but maybe 80% of the time would be sufficient. We call those properties that are allowed to be violated for some fraction of time soft properties. So note that in particular when verifying service level agreements, high precision is required. So in this example here, our imprecision has to be below 0.01% in order to verify this 4 nines reachability SLA. There is not a lot of existing work in this area. One line of work also considers probabilistic failures but solves a synthesis problem for traffic engineering in path-based wide area network routing. These works have no support for BGP or OSPF as commonly used in ISPs. Ultimately, computing the probability of the property boils down to exploring the failure space. One basic idea one could try is just exploring this space iteratively, starting with the state where we have no failures, then checking all possibilities of exactly one link failures, then continuing with all scenarios with exactly 2 link failures, and so on and so forth. So as you start to consider more and more failures, you have more and more scenarios in this class. And additionally, the probability of each such failure scenario gets exponentially less likely the further you proceed. Let's consider a network with 191 links and some realistic link failure probabilities. What is the number of scenarios you need to consider in order to verify a 4 nines SLA? In this example here, you would need more than 1 million scenarios, so this is clearly too expensive. Because imagine running an existing deterministic verifier on each of those states. Another thing you can try is probability estimation based on sampling. In this approach, you would sample from the probability distribution of failures to get a network like this, and then check whether the property holds or not. So you will continue drawing samples until you have gathered enough samples, and then compute a fraction of samples where the property holds. So we can use concentration bounds such as Hoeffding's inequality to compute how many samples we need in order to achieve a desired precision with high confidence. In our example from before, we would actually need more than 700 million samples in order to verify a 4 nines property. This is clearly also too expensive. In this talk, I will introduce NetDice, which is a probabilistic network configuration analyzer that reduces the states, in this example here, to a number of 1854, which is almost a 600 times reduction compared to partial exploration. NetDice is a probabilistic network configuration analyzer with support for BGP and IGP, high accuracy sufficient to verify 4 nines SLAs, and scalable to large networks. So how does NetDice work? As an input, it takes a network configuration consisting of router configurations supporting BGP, OSPF, ECMP, and static routes. It also accepts a powerful failure model which can express dependent link, nodes, or SLG failures. It further takes a property and then computes a probability that this property holds under the given failure model. So let's have a look at the property supported by NetDice. Consider the following network where traffic arriving at some ingress A goes towards this prefix. Note that this flow here may incorporate many TCP flows arriving at A towards the given prefix. So NetDice is interested in properties that can be decided solely based on the forwarding graph. For instance, you can check reachability by just looking at the forwarding graph of this flow. You can also check the path length of this flow or check whether it traverses some waypoint. There are many such properties, and we call those single flow properties as these only depend on the forwarding graph of a single flow. Of course, we can generalize this to multiple flows and, for instance, ask whether those two flows here are isolated. Such properties are called multi-flow properties. NetDice targets few flow properties, where we only consider a small set of flows. The exact property does not matter as long as you can implement the check based on the forwarding graph. So how does NetDice prune the space of failures? Let's introduce the key idea using this example here. This is the shortest path routing networks where all link weights are 1 except at the link in the center where the link weight is 2. So the traffic from A to B is forwarded along this path here. So let's explore some failures. If this link fails, the shortest path will change and the traffic will take a detour as indicated here. However, under this failure, the shortest path will actually not change. This is a key observation, so as long as the failure is outside the shortest path will not change, it will remain the same. So to capture this idea, we introduce the notion of cold edges. Cold edges are the set of edges whose failure are guaranteed to not change the forwarding graph, in this case all edges outside the shortest path. So in fact there are 32 scenarios which induce the same forwarding graphs. Any combination of failures of the cold edges will lead to the same graph. NetDice uses this idea to effectively prune the space of failures, as we'll see later. So the main technical contribution of NetDice is how to identify the cold edges for common routing protocols. Identifying the cold edges for shortest paths was rather easy, so let's introduce a static route as indicated in the figure. Here, traffic from A to B is first forwarded along the shortest path from A to B and is then deflected by the static route to result in the following forwarding graph. So what are the cold edges in this example? Of course, if any of the green edges fails, then the forwarding graph will change. But there are also other edges which are not called in this example. For instance, consider this failure here. In this case, A will not forward traffic to the right in the first place, as the new shortest paths from A to B looks as follows. How do we identify cold edges in this example? NetDice actually reasons about the opposite and finds edges which may not be cold. These edges are called hot edges. We have already seen that the edges on the shortest path from A to B shown here have to be hot, because if any of these fails, then the forwarding path will change. Additionally, also the edges on the remaining forwarding path have to be hot. By taking the complement, we arrive at the following 3 cold edges. Any failure of these cold edges will not change the forwarding graph in this example. Note that the set of hot edges is generally an over-approximation. It is not guaranteed that a hot edge failure will always change the forwarding graph. In contrast, it is guaranteed that a cold edge failure will not change the forwarding graph. In our paper, we provide an algorithm to obtain the cold edges for BGP. This algorithm is rather complex and I can't go into details, but there are 3 challenges one has to solve here. So first one has to take care of network partitions, because failures may disconnect routers in the BGP session topology. Second one has to take into account the special semantics of BGP route reflection. And one has to incorporate the dependency between BGP and IGP. You can have a look at our paper for details, where we also provide a correctness proof of our algorithm. So let's have a look at the failure model supported by NetICE. In NetICE, failures are modeled as a Bayesian network, which is a common representation of arbitrary discrete probability distributions and can in particular capture arbitrary dependencies. For instance, we can use this to model link and node failures. In this example here, we transform the given network topology to a Bayesian network. Each node and link in the topology is assigned a node in the Bayesian network as shown below. We connect the nodes in the Bayesian network according to their adjacency in the topology, meaning that the parents of a link are its adjacent nodes according to the topology. This results in the red dependencies. We can use this to model the fact that if any node fails, also all adjacent links fail. Similar models of failures are already used by previous work. NetICE performs inference using variable elimination, which is a well-known exact inference algorithm. Having seen the failure model, let's put all pieces together and explain how NetICE explores the space of failures. So the probability of the property holding can be unrolled as follows. We can sum over all failure scenarios the probability that the property holds given this scenario, which is either 0 or 1, because the property either does or does not hold, times the probability of the failure scenarios. This we can obtain from the failure model seen before. We can simplify this to the following sum, which sums the failure scenario probabilities for all scenarios where the property holds. We start with the scenarios where there are no failures, S0 here. Let's assume we want to check that the path length of the flow between A and P is at most 2. So first we construct a forwarding path and then check the property which holds in this case. Next, we identify the set of called edges as exemplified before. Now, the key idea of NetICE is to implicitly cover any failures of these called edges at once without having to explicitly explore them. To this end, we compute the probability mass of all equivalent failure scenarios. In this case here, this is equal to the probability that the two green links are not failing. In this example, let's assume this probability is 0.62. Note that this probability is way higher than the probability of the no failure state alone, as it involves also many more failure scenarios. Now, we simply have to explore the remaining states by introducing failure to the hot edges. So, we will for instance let this link here fail, and then we can again construct a forwarding graph and check the property, which does not hold in this example. We will also let the remaining link fail, construct a forwarding graph and check the property. Now you can imagine that you can recursively always construct a set of called edges and so on and so forth, as we have just seen it. There's one important thing to note here. We have to make sure that we don't explore failures twice in this tree. For this, we have to ensure that the indicated link here does not fail in the subtree of S2, because this failure is already explored in the subtree of S1. At the high level, failure exploration visits a tree of scenarios and finds equivalence classes of scenarios where the property holds. We simply have to sum up the probability of those scenarios to obtain the probability of the property holding. As an optimization, we can cut off unlikely scenarios and stop exploration when the probabilities gets very small. As a result, we get a lower bound on the property probability. The efficiency of our approach depends on the number of called edges. If there are no called edges, our approach is equivalent to partial exploration, but if there are many called edges, we can prune the failure space effectively. In practice, this is indeed very efficient. So how efficient is it? We implemented our approach in NetDice and published its code on GitHub. You can have a look. The implementation supports a small set of predefined properties including reachability, path length, egress, waypointing, isolation, load balancing, and a basic form of congestion. You can easily add your own property by implementing a check based on the forwarding graph. For our evaluation, we take 90 topologies from previous work. The resulting set of topologies includes networks between 50 and 2320 links. We use a realistic failure model, which we also obtained from previous work. We use synthetic BGP configurations with 2 route reflectors and 10 border routers, though we also analyze other configurations in our paper. We also analyze a real ISP configuration. For details, please have a look at our paper. We analyze the signal flow waypoint property on all the topologies up to a 4/9 precision. In this graph here, you see the number of links on the x-axis and the inference time on the y-axis, where the gray top bar indicates a 1-hour timeout. So as you can see in the graph, even for networks with hundreds of links, NetDice only requires few minutes to verify the properties and is hence very efficient. We observed that for 80% of the visited scenarios, more than half of the links are called. This explains why NetDice failure pruning is so effective. So let's see the impact of increasing the number of flows under consideration. Here we consider a single network of 235 links and analyze a basic congestion property using an increasing number of flows. As you can see, the runtime increases the more and more flows you add. So NetDice is efficient for few flows and its performance degrades gracefully when considering more and more flows. In the paper you find more details about our evaluation. So with that, I would like to summarize. We have seen NetDice, which takes as input a set of network configurations, an expressive failure model, and a property to compute the probability that the property holds in the network. NetDice uses the key idea of cold edges to effectively prune the failure state and explore it in an efficient manner. NetDice is publicly available on GitHub, supports BGP and common IGPs, and can be used for accurate analysis.